Introduction to Differential Equations. So we'll start with what is the meaning of integration, or what's its purpose. So there are several meanings to it. The first one is just seeing it as a mathematical operation. So it's the opposite operation to differentiation. So we could call it anti-differentiation. This is much in the same way as subtraction is the opposite to addition, division is the opposite to multiplication, inverse cos is the opposite operation to cos, and so on and so forth. Square root is the opposite operation to something squared. So just as a mathematical operation, and that's how we'll treat it today, just to get you familiar with the type of questions we'll be doing. The second meaning is, we know that from differentiation, if you differentiate a function, it gives you another function that relates the slope of the tangent at any point along the given curve. So if you were given the equation that described the slope of the tangents to all of the curves, then if you integrated that, that would give you the actual curve itself. So it's working backwards again after differentiation back to the original function. The third thing it could be, or could be used for, is the area under a line or a curve. Or we saw in moment of inertia, we used it to get the area of a shape, or we used to sum up an area of a shape. That brings us to 4 then. Integration is an infinite sum. So we use that as well as an explanation for why we went for a summation sign to an integral sign in moment of inertia. And what we're saying there is, if we want the area of a particular shape or the area under a curve, we break it up into a certain number of sections. That will give us an estimation. There's your summation symbol. And then when you make those sections infinitely small, you get infinitely many of those sections, and then your summation turns to an integral sign. And 5 then, depending on the context, it can mean different things. So we'll see integration in nuclear physics, nuclear decay, populations. We'll see it in business. We'll see it in cooling and a few other different places. And the integration, after we integrate it, each of the things that we obtain will mean something else within those contexts. So it's a mathematical tool that can do a few things. But for us, we're just going to use it as anti-differentiation just for the time being. Okay, so your best friend for today, and probably the next day as well, will be page 26 of the log tables. These are the standard integrals. And we have 3 columns there. The left-hand column are the ones that are the relatively easier ones, and they pop up very often. So the first one is x to any power. When you want to integrate it, you add 1 to the power and divide by the new power. So if you had x cubed, then what you'd do is you'd add 1 to it, you divide by it, and the integral of x cubed would be x to the power of 4 divided by 4. Just as an example, you've probably seen that already. The second one is very typical of stuff you'd see in differential equations. So if you integrated 1 over x with respect to dx, your answer there would be natural log of x. So that's log to the base e of x, and we take the absolute value of the x value. If you integrate e to the power of x with respect to dx, you'd also get e to the power of x. If you integrated e to the power of ax, where a is a constant and x is a variable with respect to dx, the function that you'd get would be 1 over a e to the power of ax, and so on with the rest of them. So cos of x, when you integrate it, goes to sine of x goes to minus cos, and so on. The middle column, these ones I find guys have a difficulty identifying them, and also they have difficulty with the last 2 in the middle column, as well as the 4 on the right hand column, identifying which standard integral to use. So we might spend a bit of time doing many of those questions, but today you'll see 1 or 2 of them just so you can see how to approach them. And then underneath the box we have integration by parts. That's been taken off the Applied Maths Leaving Cert syllabus, because I think it might have been taken off the no, I think it's taken off the Leaving Cert Applied Maths syllabus, but I'll have to verify that. Okay, so the first thing we're going to do is look at the top 4. So we're just going to pick from the top 4 there, and we'll start with the question as follows. So solve the differential equation if y is equal to 1 and x is equal to 2. So 1 over y multiplied by dy dx equals x plus 1 over x squared. So what I want to do is I want to make sure that everything with y and dy is on one side, everything with x and dx is on the other. And I cross multiply to make that happen. Now, I'm emphasizing the following point. Multiplication and division is the only way you can separate this out. Please don't use addition and subtraction, except in extreme circumstances, like you have to rearrange and take an x from the left to the right there or something. So multiplication and division is your main focus here. So if you look at the function, what I've done there is instead of 1 over x squared, I've written that as x to the minus 2. And then what I want to do is bring the dx over, so if I multiply both sides by dx, I'd be left with 1 over y dy, and x plus x to the minus 2 all multiplied by dx. Now we can't have dy's and dx's on their own, so we have to have the integration sign as well. So the script s on either side. And that means our differential equation can be written in a form whereby we can use anti-differentiation to solve for it. So the integral of 1 over y dy equals the integral of x plus x to the minus 2 dx. On the left hand side, that's in the log tables, that will work out as the natural log of y. On the right hand side, we'll have to integrate both terms with respect to dx. So x to the power of 1, add 1 to the power, divide by the new power, and then we'll do the same to x to the minus 2, add 1 to the power, divide by the new power. That will give us the following. So I've restated the line there, and in the second one we get natural log of y is equal to x squared over 2 minus x to the minus 1 plus c. And that's the general solution. You need to include the constant in there. And very often I get a question, why isn't there a c on both sides? Well, ideally there should be. So I should have natural log of y plus c1 is equal to x squared over 2 minus x to the minus 1 plus c2. But what I've done is I've taken the c1 over to the right, and c2 minus c1 I've just rewritten as a constant, capital C. So I replaced two constants with one value on the right hand side. Now, if you look at the top box, it says solve the differential equation if y is equal to 1 when x equals 2. So x equals 2 and y is equal to 1 are what we call our initial conditions. And I need to sub those into the general solution, get a value for c, and once I have a value for c, I put that value into the equation to get my specific solution. So IC for initial conditions when y is equal to 1 and x equals 2. Sub those into the general solution, I get c is equal to minus 3 over 2. And that means I get the natural log of x over 2 minus 1 over x minus 3 over 2. That's my specific solution. And look, the last thing that I need to do is rewrite that to make y the subject of the equation. In other words, just have y on the left hand side. So when I rearrange that, I get y is equal to e to the power of all of that thing there. So that's example 1. Example 2, let's go back to the log tables. In example 2, we'll use these ones here. So some of the trig functions. It'll also use the ones above, but we've seen those already. Specifically, when you integrate sine x, you get minus cos x. So question 2. I have dy dx is equal to sine x over e to the power of y, and I'm given my initial conditions again. So the first thing I need to do is cross multiply to get everything with y on one side, everything with x on the other. So I've done that. E to the y dy equals the integral of sine x dx. Integrate the left hand side, we get e to the y. Integrate the right hand side, we get minus cos x. And I need a constant there somewhere. I put it on the right hand side. That's my general solution. Sub in your initial conditions to get the value for c. So we sub those in, we get c equals 2. And that means that my specific solution is e to the power of y is equal to minus cos x plus 2. Now again, make y the subject of the equation. The only way to get that power down is to multiply both sides by the natural log. So I get the natural log of the left equals the natural log of the right. I have the natural log of e to a power, meaning I can take the power out in front. So y times the natural log of e is equal to the natural log of 2 minus cos x. And then the natural log of e to the base e is 1, so I get y on its own on the left hand side. Okay, example 3. Example 3, we'll use a variation of that. So I might actually state this fee elsewhere, but if you have 1 over x plus a, when you integrate it with respect to dx, you get the natural log of x plus a. All right, and I'll show you that probably at another date. Okay, so we've got kind of a complicated thing here. we have 1 plus x multiplied by dy dx equals 1 over y plus 3. Cross multiply, so the y plus 3 will go up to the top left, the 1 minus x will go to the bottom right, and the dx will go on top. Okay, so that's the second line there. Now we need to integrate it. So there's a couple of things I've done here. On the second line on the right hand side, you'd see equals 1 over 1 minus x dx. And what I've done is I've taken a minus out of that term there. So I end up with minus the integral of 1 over x minus 1 dx. Now there's a reason for that I'm not going to get into right now. I'll do the switchy the next day. So if we integrate the left we need to integrate the y and the 3 with respect to dy. So add 1 to the power, divide by the new power, we get those values. And then when we integrate the right hand side, 1 over x dx as an integral becomes ln of x. So the integral of 1 over x minus 1 becomes the ln of x minus 1. There's a little bit of mathemagic going on there. Just go with it for now, and I'll explain it in more detail soon, right? So we have our general solution. Sub in your initial conditions. You get a c value, c is equal to 0. And then you get that equation in the box there. Now, what we have there is a quadratic. You've got something with y squared, y, and you have something with x there that eventually will become a constant. And the reason it becomes a constant is right back up at the top of the screen. We're looking for if that differential equation with the initial conditions, find the value of y when x equals minus 2. So what we're expected to do with that specific solution is put in x equals minus 2. That will give us a quadratic, and then we can solve the quadratic for both values of y. So pause the video, and will you sub in the minus 2 and solve for the value of y, please. I'm going to keep going. Question 4. Let's go and use that one. So what I want you to note here is it's 1 over something squared, which is the x squared thing. So that's the variable, plus a constant squared. And then what we get when we integrate it is 1 over the constant inverse tan of the x value over that constant. So let's have a look. So we have dy dx is equal to 1 over x squared plus 4, and we're given initial conditions. We're looking at the standard integral. So what I need to do is rewrite it as the integral of dy equals 1 over x squared plus 2 squared dx. So comparing it to the standard integral, the a value is equal to 2. So I'm going to get 1 over 2 inverse tan of x over 2. All right, on the left we get y then as well. Fill in your initial conditions, get a c value, and then sub that in, and that's your answer.